Okay, so thank you very much for the organizers for inviting me here. This talk is basically going to be a continuation of a couple of talks that you heard yesterday from Kyriakos and from Joe, and it's based on these three papers which we wrote with Kyriakos, and also on work in progress with postdoc at ICTS TIFR in Bangalore, who's Prashant Samantre, and a postdoc with Kyriakos, who's Shouvik Banerjee. So let me start by giving you a summary of what I'm going to say. And as you've heard a lot over the past couple of years, usually we have this naive expectation that if you put together effective field theory and gravity, and you put together just quantum field theory and curved space, then strong quantum gravity effects are confined to some Planck scale region near the horizon. But as all of you know, there's been a lot of recent work on the information paradox that suggests that the information paradox is so severe that to try and resolve it, you actually have to drop this robust assumption, and you have to allow quantum effects to spread all the way out so that they spoil the structure of the horizon. And what I'm going to try and tell you in this talk is that this construction of the black hole interior in ADS-CFT that Kyriakos described yesterday helps to resolve all of these arguments, and it really helps to resolve all of these arguments, and it sidesteps all of these arguments for structure at the black hole horizon, and I'm going to try and describe that. But it sets up its own set of issues, including this issue of state dependence that Joe mentioned in his talk yesterday, and so I'll end my talk by talking about that. Okay. So this is an outline of what I'm going to say. I'll start by very quickly reviewing this construction of the black hole interior that Kyriakos described yesterday. I'll talk about how these state dependent operators, if we construct, help in resolving all of these arguments that pertain to the information paradox that have come up in the past few years. I'll talk about non-equilibrium states, and the reason this is important is because this tends to push our construction towards a regime where you might potentially see an ambiguity, so I'll talk about that, and then I'll conclude with some discussion of open questions, including the issue of state dependence that was discussed a lot yesterday. So let me start by reviewing this whole story of our construction of the interior. And the basic idea in the construction of the interior is that over the past several years, using the work of many people, we have an understanding of how to construct local bulk operators using boundary operators. And the essential point is that in the bulk there are both left and right moving modes for a quantum field, and outside the horizon both these left and right moving modes are supplied by the usual ADS-CFT dictionary by ordinary single trace operators on the boundary. However, while these left moving modes cross over smoothly across the horizon, the right moving modes don't. And so to construct a good local operator behind the horizon, you need some new degrees of freedom that supply these right moving modes. Okay? And that's what we call these mirror operators. And we can actually say something rather precise about these mirror operators. There's some rather precise kind of equation we can write down. So not only do you need these new operators, they have to have a particular kind of interplay with the ordinary operators, and there's some equation you can write down which roughly says that if you sandwich together some of these ordinary operators, which I'll call O, and some of these mirror operators, which I'll call tilde O, and you sandwich together some product of these operators in a typical state, then what you should get is something that looks pretty similar to the thermal ensemble, but the mirror operators need to float to the right of all the ordinary operators, so they need to commute with the ordinary operators, but not, in addition, they also need to behave like the adjoint of the ordinary operators, but analytically continued. Okay? So it's a deceptively simple equation, but nevertheless it's a precise condition we can write down that tells us, what we need to construct a local field in the interior of the black hole. Okay? How do we construct these operators? Kyriakos described this construction yesterday, and the basic way we construct these operators is first to start off with some state. You start off with some state of the black hole, and then you consider all possible ways in which you can excite this state. So you consider all possible reasonable experiments you can make about this state. All possible reasonable experiments are given by products of ordinary single trace operators in the boundary. So that's this set of this set of products. And and then given the equation that I showed you in the previous slide, that tells us, that gives you a particular prescription for how these mirror operators needs to act not only on this basis microstate that you started with, but also this basis microstate excited with all these possible reasonable experiments that you can do. And this gives rise to some set of linear equations, and the key point is that the number of reasonable experiments that you can do is actually much smaller than the dimension of the Hilbert space. Okay? The dimension of the Hilbert space is e to the n squared, but if you're doing reasonable experiments, low energy experiments, you can't do e e to the n squared different experiments. You can't have e to the n squared different reasonable operators to excite the microstate with. And so for all except for a measure 0 set of these states, we can actually solve these equations, and there is an explicit solution for these equations, and that allows us to construct these mirror operators that satisfy the properties that I said they had to satisfy in order to construct a local field behind the black hole horizon. So that's the essence of our construction. Okay. Let me start off immediately by saying a few words about state dependence. In what sense are these operators state dependent? They are state dependent in the sense that you start off with some black hole microstate, and as I said, you consider some neighborhood of the microstate which is obtained by exciting this microstate with various operators, and these operators have the property that they act correctly within this neighborhood of the initial state that you started with. Okay. However, if you make a big change in your black hole so that you go to a totally different part of the Hilbert space where your black hole microstate is completely different, then if you want to describe the same operator in the bulk, inverted commas, if you want to describe the same operator at some point behind the horizon, then you need a different operator in the CFT Hilbert space to describe what you would naively have called the same operator in the black hole background. So in this sense, these operators are state dependent. However, once you've settled down to some microstate, and if you're probing the neighborhood of that microstate, then you can multiply these operators, use the Bond rule, take correlation functions, and do what you would usually do with linear operators. So this is something that's useful to recognize. Okay. Now, let me go on to these firewall arguments. So this construction of black hole operators immediately brings us into conflict with a lot of this work that has gone on in the past few years that suggests that there should be structure at the black hole horizon. And if I had to paraphrase in a precise way, if I had to paraphrase in one line, the essence of all of these arguments for structure at the black hole horizon, I would paraphrase them by saying that these various arguments, and they're very good arguments and nice arguments using counting and genericity of commutators and using other such arguments, give us various reasons why the CFT Hilbert space does not have enough space to accommodate these mirror operators. Okay. So if I had to give you a one-line precise phrasing of all of these arguments, these are various arguments suggesting, general arguments of course, suggesting that whatever you do, there's no way you can construct mirror operators with the properties that I demanded at the beginning. Okay, and I'll review some of these arguments a little later. But what I want to do in this talk primarily is to review how our construction of the mirror operators sidesteps a lot of these arguments, and I think this is useful both to understand some of the hidden assumptions in these arguments, but also to understand some of the peculiarities of the construction that were alluded to yesterday, and so I think both these exercises are useful. Okay. So let me start with the first argument, which is perhaps the most well-known one, which is what's called the strong subadditivity paradox. So the strong subadditivity paradox is basically the following. You consider an old black hole in flat space, and you have this black hole, and you have some old radiation, which I'll call A, and there's some Hawking bit that's being emitted from the black hole at the time that you're examining it, and the bit that's falling out I call B, and the bit that's falling in I call C. Okay? And now very general arguments due to Page that Joe reviewed yesterday suggest that this bit B must be entangled with the early radiation. However, if the horizon has to be smooth, then this bit B also has to be entangled with this bit inside the black hole, which is C. Okay? But the strong subadditivity in this case, is a statement of the monogamy of entanglement, which says that this B can't be entangled both with C and with A, and that leads to an order 1 contradiction with a rather general theorem in quantum information theory, and I want to emphasize that it's an order 1 contradiction. It's not something you can get rid of by using small corrections, if this is really applicable. Okay? So what is our resolution to that? Our resolution to that is basically that these three subsystems, the old radiation and the radiation in the zone of the black hole and the radiation just behind the horizon of the black hole do not constitute three independent subsystems. That's our resolution to that. And in fact, we have a mathematically precise realization of that resolution, which is that if you take these mirror operators and you construct them using the algorithm that I mentioned, and you work out the commutator of these operators O that describe the degrees of freedom outside with these operators O tilde that describe the degrees of freedom inside, that commutator is non-zero. And that's a statement of the fact that these degrees of freedom are not independent. It's a precise statement of the fact that these degrees of freedom are not independent. And I should say that this is consistent with old notions of complementarity and even other resolutions that were proposed before our, even before our work, and this was what was called A equal to RB by very many authors. Okay? This is what's sometimes called the A equal to RB resolution. However, the AMPS collaboration was aware of these arguments, and so they had a counter argument, and it's actually a very powerful counter argument. And the counter argument is basically the following. It's the statement that, if you try and embed the interior, as I said, in the exterior in some naive way, then generically you end up with this commutator not only being, some non-zero operator, but also being generically something that's order 1. And this is something you can easily persuade yourself of by doing some numerical experiments in Mathematica. Take some big Hilbert space, think of some operator that acts in this Hilbert space, take some random unitary operator in this big Hilbert space, and scramble, this operator outside using this random unitary operator. And you might think that, given that your Hilbert space is so big, you had some operator that was acting on some part of the Hilbert space. Now you scrambled it with this huge matrix. So, presumably this new operator is acting in a different part of the Hilbert space. And so maybe these two guys should commute. And in fact, it is true that if you look at the matrix elements of this new operator that you get in this manner, these matrix elements will indeed be very small. However, the catch is that these matrices that you're considering are very large. And therefore, if you consider in this typical state, in some typical state, the square of this commutator, not just the expectation value of the commutator, but the square of the commutator, this is typically some order 1 quantity. Okay? And that is actually a problem. The reason that is a problem is that if it were true that operators inside, quantum fields inside had some order 1 commutator with quantum fields outside, then these two friends who live across the horizon could send messages to each other. Okay. So, the generic commutator, which is something that turns out to be order 1, as I explained, is a very powerful argument against the use of complementarity to resolve the firewall, and it's something that certainly played a lot of, played a huge role in our own work. And I think any resolution to this firewall has to deal with this problem, and this is something that's important to recognize. So, how do we get rid of this? The way we get rid of this is as follows. It's true that the commutator that we have is non-zero. However, it's cleverly designed so that it happens to be 0 precisely on the typical microstate and on excitations of the microstate by all these ordinary operators. And you can check this using these linear equations that I showed you before that these operators are designed to satisfy. So, you can check that it exactly annihilates. It doesn't take it to something else. It's designed to annihilate, the state and all excitations of these states of the state by reasonable operators. And what this means is that this commutator is completely undetectable in low point correlators. And we have a notation for this, which is that you say this commutator is equal to 0, but with a dot on top, which means that it's effectively equal to 0. No low energy observer can measure this commutator, but it's actually not 0 on the full Hilbert space. And that becomes important when you consider things like the von Neumann entropy, some very fine-grained observable. Okay. Good. Now, what are some of the other arguments that suggest that you can't construct these C tilde operators? A very nice and elegant argument is this argument which is sometimes called the counting argument, which goes as follows. Imagine the black hole in some Hartle-Hawking state. Now, in this Hartle-Hawking state, think of this creation operator that I talked about. You have to take these O tilde operators and normalize them in some particular way. But think of this creation operator behind the black hole horizon. But creating an operator behind the horizon, you can easily persuade yourself in the Hartle-Hawking state, is like destroying an operator in front of it. What this means is that the creation operator has negative energy actually as measured from the CFT. However, you also expect that the creation and annihilation operators satisfy some usual algebra of simple harmonic oscillators. And what that algebra tells you is that these creation operators have to have a left inverse. However, an operator that lowers the energy in some theory which has a monotonic growth of states with energy, can't have a left inverse because it has to annihilate some states by virtue of having the property that it lowers the energy. And so this suggests in a very general fashion that you can't have these creation operators behind the horizon, and hence you can't have a black hole interior at all in ADS-CFT, even for big black holes. Forget about evaporating black holes in flat space. This argument applies even to big black holes. Okay, what's our resolution for this? Our resolution for this is actually again the same. It's the statement that the action of these operators, the fact that they satisfy the simple harmonic oscillator algebra is correct only about this base microstate that we started with and about all other low energy excitations of this microstate that you can do. Okay, that's our resolution to this. And once again, you can see this rather precisely, and it's again the same dot equal to sign that this algebra is not, this commutator is not really 1. Okay, but it is 1, it appears to be 1 for any low energy observer who is exciting the state psi with some reasonable light operator AP. Okay, and so that's again the resolution. And if this commutator doesn't have to be 1, then there's no reason for these operators to have a left inverse. So it's once again the same resolution. there was one more argument that was produced by Marolf and Polchinski that Joe talked about at some length yesterday, which was the argument that, if you think of some fixed operator O tilde omega, then again very general arguments which I won't review, but I'm glad to do in the questions if someone has them, suggest that the expectation value of the number operators measured by some infalling observer is actually 1. Okay? However, because we have a construction of these local quantum fields, we can actually write down some concrete expression for this number operator, and this number operator, it's some Bogoliubov transform of the usual modes, and because of this fact that I mentioned that, the mirror creation operator acts like the destruction operator, the ordinary destruction operator, you can compute this number operator, on a state, and you find that it's 0. Okay. So, our construction ensures that the infalling observer measures no particles, and this is again, as a result of the fact that some of there's a particular technical change of basis they made in the arguments which doesn't apply to operators of this kind. Okay. So, once again it gets around this once again. Yes. Yes, I will talk about state dependence. I will talk about it. I have several slides. Please, John. I will certainly talk about it. Yes. Okay. Thank you. Okay. Let me give you an interim summary before that. Okay. So the interim summary of this is that the use of an appropriately, defined state-dependent mapping between the bulk and the boundary, addresses all of these recent information theoretic arguments for structure of the horizon. And I'm going to talk about some of the peculiarities of the mapping. Okay. But it's true that if you are allowed to use operators of this kind, then it does address all of these arguments for structure at the horizon. Okay, good. Let me turn to a few more features and bugs of this construction. For example, here's a question that some people have asked us, Samir Mathur, for example. And our construction suggests that, if you look at endpoint correlators, these endpoints don't have to be closed, but if you separate them and keep them separated in ADS, then our notion of locality breaks down. Remember I said, this commutator was non-zero, you couldn't detect it within a low point correlator, but you can detect it within an endpoint correlator. Okay? Is there some independent evidence for this fact that locality completely breaks down if I start measuring some endpoint correlation function in ADS? Actually there is, and it's important to recognize, what is the kind of evidence you could give for the breakdown of locality in ADS CFT, and it's important to recognize that, the CFT, all observables in the CFT that permit a local description are those which simultaneously permit a 1 over n expansion. And the reason for that is if you think of the bulk path integral, then some semi-classical space-time is a saddle point of this path integral and about which you can do a good 1 over n expansion. So what you really need to argue is that the 1 over n expansion breaks down for for endpoint correlators, and that would then be a good argument, that would be independent evidence for the fact that locality breaks down for these endpoint correlators. You can actually do this with some crude counting of Feynman diagrams. If you think of some tree level bulk connected amplitude, it's important you're thinking of the connected amplitudes and not the kind of things that were done earlier when you considered baryons at large n, where most particles just pass through each other. But if you think of a connected endpoint amplitude, such an amplitude receives contributions from about n factorial diagrams, and it's suppressed by some large power, the coupling constant. This is still a very small quantity, 1 by n to the n into n factorial is still e to the minus n. However, if you now think of the one loop amplitude, the one loop amplitude is suppressed by some additional power of the coupling constant. It's suppressed by an additional 1 by n squared, but there are more one loop diagrams than there are tree level diagrams, and it's easy to count this. You think of the possible cuts of one loop diagrams, and you cut them into p legs on one side and q minus p legs on the other side, and you can count the number of such diagrams, and the number of such diagrams is in fact precisely enhanced by the number of external legs that you have. And so you see, if you start considering endpoint amplitudes, then the one loop amplitude, the connected amplitude, becomes as important as a tree level contribution. And so, even if you're at large n, your 1 over n amplitude counting breaks down, and so locality breaks down. And this is an independent evidence of something that's, in some sense predicted by a construction. Okay. Let me now talk a little bit about equilibrium states. The reason equilibrium states are important actually is because they push our construction into a regime where there might be a potential ambiguity. Before I talk about, how you go away from equilibrium to non-equilibrium states, let me just try and tell you what we mean by equilibrium. So at least, we don't have a very precise definition of criteria to identify when a black hole is really in equilibrium and has a smooth horizon, but one necessary condition is the time independence of correlation functions in the boundary. So you measure correlation functions at some time, you translate both times up by some amount, and those correlation functions have to be time translationally invariant, and that's one necessary condition that these correlation functions have to satisfy. So now, yes. So now what happens, if you think of a state that's out of equilibrium, it shouldn't be that our construction always tells you that you see no particles, because clearly there are some situations where you do see particles, which would be a situation where someone shines a laser beam just before you jump in. That would be a situation where you take this, this microstate that I had, which was in equilibrium, and excite it with some unitary operator. However, using the criteria I mentioned in the previous slide, this time independence criteria, you can actually not only detect that you have excited the state, you can actually even detect what was the U you used to excite the state, at least as long as the unitary operators are of this particular form, which we call near equilibrium states. And I can use this and I can improve my definition of my mirror operators so that I once again reproduce semi-classical expectations, which are that this time for this non-equilibrium state I will see particles at the horizon. Okay, good. Now I can do something slightly more perverse if I am more perverse. And to do something more perverse, I can set off a beam not from in front of the horizon but behind the horizon. However, the point is that I can smoke on my pipe and I have this Hamiltonian in my hand, I have another operator in my hand, and my Hamiltonian registers a jump the moment you turn on a source behind the horizon because you added some mass to the black hole, and that is something I can detect even at infinity. And so if I am allowed to measure correlation functions of ordinary operators with the Hamiltonian correlation functions of these kinds, these are things that for equilibrium states would have been exponentially small, but for these kinds of perverse non-equilibrium states actually are something calculable and are something we can use to again detect and improve our construction. However, you can do something even more perverse, and this is something that Daniel Harlow has pointed out, which is to not use our mirror operators, but use some slightly different operators that create excitations behind the black hole horizon without adding to the mass of the black hole. So they pull energy out of the infalling matter, which is somewhere far away, and bring it close to the horizon. Now these are things that for technical reasons actually you can't define an energy eigenstates, and in fact they are also things that are for this reason they don't behave like ordinary creation operators which create some energy whenever they create a particle. However, we don't have an understanding of these, and if you were perverse enough to excite the black hole in this way, we don't yet have a good understanding of how to detect and identify these states. Okay? I should say though that this is a problem that's independent of our construction. Even before all of the recent fuzz, fire and complementarity debates, everyone would have agreed that there's an exponentially small fraction of states which are out of equilibrium, where the horizon is actually excited because the star, as the star was collapsing, some part of the star broke off and started floating right next to the horizon at ultra-relativistic speeds. Okay? And in fact, if you just give me a microstate, it's very hard to detect which microstate is of this form and which microstate is not. And so I think this ambiguity is something that's broader, goes beyond our construction, is something that's important to understand in ADS-CFD in general. Okay? That being said, let me turn now to this issue of state dependence that Joe was mentioning. And this issue of this ambiguity brings us to a broader question which has to do with the structure of our operators in general. So as I said, the operators that we have are defined in some local patch of the Hilbert space, and in general if you are allowed to use some state dependent operators, that's a very nice earlier work in fact which Joe was involved with also, and there were other people including Jason, and this was in the context of this nonlinear quantum mechanics that Weinberg proposed, and they pointed out that if you entangle these systems and if you are allowed to measure these arbitrary kinds of operators, you could send superluminal signals, so you could do something even more bizarre where you could communicate between different branches of the wave function and so on. However, there are a couple of important differences in this case. You might imagine that because of these properties actually, your bulk theory would be completely uncontrolled. But it's important to recognize that we have a perfectly ordinary boundary theory that we can use as an anchor to understand time evolution, and that's something that's an important difference in this case. Also, it's true that we need to understand better what happens when the CFT is entangled in some other systems, but I think it's fair to say that no one has really produced the kind of thought experiments that Joe and others produced at the time of Weinberg's nonlinear quantum mechanics that give a sharp contradiction with any such principles. But however, I want to say something stronger, which is that these operators that you're measuring are actually local operators in quantum gravity, and so in fact this kind of behavior that I've been describing might not actually be all that unexpected. Okay? And why is that? The issue is, if you are looking at what's called a local operator, this is something that's actually not gauge invariant in quantum gravity, but the question is whether you should be able to position it in some state independent manner. And you might say, let me start from the boundary and let me jump for some time t, let me fall in for some time t, and then let me measure the field at that point. However, if the metric was of a very different form, corresponded to some very different state, actually you might end up well behind the horizon. And in fact, we can show, and it's not very hard to persuade yourself, that the precise effects of a firewall can be mimicked by mispositioning operators. You know, if I give you a set of correlation functions and I don't tell you what points those correlation functions are tied to, you can very easily persuade yourself that this is precisely what corresponds to a firewall. But what might have happened is that, well, you know, the 2-point function that you identified as corresponding to a firewall in fact just correspond to some mispositioned bulk probes. When you are measuring 2 points that were right next to the horizon, you were actually measuring something very different. And this is something that can happen, and this is something that's important to understand. You know, can you really position operators in some state-independent manner? And one thing that Joe mentioned yesterday, last couple of, so one thing that Joe mentioned yesterday, which was, you know, you can do this actually in some other ordinary systems, and you might try and do this by putting some projection operators. You know, you might say, let me think of the set of all possible coherent states, put projectors onto those coherent states, and then use that, you know, to transfer my boundary operators to the bulk. However, the point is, as many people pointed out, including Luboš Mottl in a very nice blog post, these coherent state, well, it's true, it is a very nice blog post actually, and the thing is that these coherent state projectors are not orthogonal. And because you have so many semi-classical solutions, in fact, it's pretty hard to prove that this kind of an operator is actually behaves the way you want. That when you insert it in a state which has a good semi-classical interpretation, it has the properties that you'd expect of a local operator. And even if you could prove this outside the black hole, which has not been done, I think it would be a slightly more difficult exercise to prove that you should expect such behavior to continue behind the black hole. And I want to mention that this is actually consistent with the lore that there are no background independent operators, local operators in quantum gravity. Okay, so I'm mostly done. Let me just say one thing, it's one thing to finish, which is that, you know, the necessity of these state dependent bulk boundary maps to smoothen the horizon and to resolve the firewall seems to be one of the key lessons that has come out of this firewall debate. And you know, either you accept, if you want to get rid of the firewalls, you have to accept these kinds of maps. And I think this issue of state dependence is leading us to a broader question that has broader interest in quantum gravity, which is how do we really describe local observables in quantum gravity? And I think this is really forcing us to confront that question. And I think this is a question that's of broader interest. Hopefully, we'll have more to say about this next year at Strings 2015, which is at our institute in Bangalore, and this is our campus. So I hope all of you come there and we'll have more to say about local operators in quantum gravity.